Bismillahirrahmanirrahim. As you know that the chapter which is going on is the subsurface flow considerations in the barrage design. And what are the two main problems or issues created by the subsurface flow of water under the hydraulic structure? What are the two main problems? तो क्या है?
The uplift pressure or seepage flow.
नहीं, seepage flow तो है ही.
Undermining.
Seepage flow
Undermining.
दो problem. Yes. One is the uplift pressure and the second is
Piping,
undermining or piping. Uplift pressure means the water will apply pressure, uplift pressure here on the hydraulic structure. And secondly, there would be undermining. The fine particles from the soil may move due to the seepage force which the seepage water applies, and then those fine particles, they emerge on the downstream of the structure. And if this process continuously takes place for a longer time, and if it is not checked, and if we don't do its solution, then what happens? You know, the porosity of the soil under the hydraulic structure is keep on reducing or increasing. The porosity will increase. It will become more porous. And when the porosity will increase, and due to this load of the structure, there will be collapse of the soil and ultimately the collapse of the hydraulic structure, particularly due to undermining. The downstream part of the hydraulic structure starts failing first. Okay. And then ultimately it may fail only the downstream part or the whole part, and that is the role of the undermining or piping. So anyway, these two issues which are always produced by the subsurface flow. So certain theories were presented by the engineers, by the researchers, and those who give the solution of these two problems. There were two creep theories and one Khosla theory. Okay, so all these, how to compute the uplift pressure and how to compute the undermining. So we discussed these all, I think, if the Khosla has given three cases. In case one, there is a sheet pile either on upstream side or on the downstream side, and you can compute or determine the uplift pressures at point D1 and point C1, and also on point E and on point D. Okay, just as a common sense, now what I would like to ask you, where the uplift pressure would be more, at point C1 or at point E?
So at point C1.
The uplift pressure would be more. And
yes,
why
sir.
At point E, the uplift pressure would be lower? What is the reason?
Sir, because it is the downstream side.
Yeah, then so what? Yes.
Sir,
Sorry?
Sir, head loss की वजह से, sir.
Yes, head loss increases as the water moves in downstream direction. So due to higher head loss, the uplift pressure at point E is lower as compared to at point C1. Okay, and these are the equations which are given to compute the uplift pressure by Khosla. And this we discussed in the previous lecture, that there are 6 points along the sheet piles, but the equations given are only 4. So what was the reason? What was the reason?
So he shared the same reason. He says that at the upstream side, maybe it is point A. So he said there is the maximum uplift pressure, and at point C, because he has not given the equation of C, so he said it at the downstream side, outside the sheet pile, there will be the negligible or zero uplift pressure.
Yes, because at point E1 and at point C, the residual heads would be equal to the acting heads. Okay, like here it is, if this is the capital H, so here the uplift pressure would be capital H. And here, if there is, let's say the depth of water is H1, small h1, then the head would be small h1. Or if there is no water, the head would be 0. Okay, so because these two are known, already known, so whatever is the heads available on the upstream side and on downstream side, same are the uplift pressures, so equations are not required. And then this was the case 2, in which there is instead of negligible thickness of the concrete floor, there is a thickness of concrete floor equal to small d. Then how you can compute the uplift pressure here and the uplift pressure at point D1 dash. Okay, and the same is the case here, how you can compute uplift pressure at E point, D point, and the C point from here. Anyway, after discussing the equations, the next thing which we need to understand are the cost loss curves. As you know, those equations we can apply. It doesn't matter. But instead of using those equations, we can directly use these curves. Actually, these curves are basically the plots of those equations for various values of D over P and B1 over B ratio. Okay, and for various values of these D over B, so what the Khosla has done, he has plotted these curves, and on y-axis he has given the uplift pressures in terms of percentage, where so there are two y-axis. This is the main y-axis, this may be the secondary y-axis, but the both y-axes, they give the uplift pressure heads, whereas the x-axis could be 2 for case number 1. The x-axis is D over B. By the way, what is D over B? D is the length of the sheet pile, and B is the length of the impermeable floor or concrete floor, which is this one. Okay. If it is the case number 2, in which we are considering too much or adequate thickness of the concrete floor equal to small d, then again the D over B would be this D divided by B. And if we are considering some intermediate sheet pile, then what we can do, we can use these graphs, and here on the basis of ratio of B1 over B, where B1 is the, the length of the concrete floor up to the intermediate sheet pile, whereas the small b is the total length of the impervious concrete floor. So using only computing this D over B and B1 over B, we can solve the issue of computing the uplift pressures very quickly. Is it okay?
सर ये इंटरमीडिएट शीट पाइल तक जो डिस्टेंसेस जा रहे हैं B1 और B2, ये इनकी स्टार्टिंग कहाँ से हो रही है?
Yes, of course. If this is the total length of the impervious floor or concrete floor, horizontal floor दिखाया हुआ है यहाँ पे, So this one would be the B1. B1 means this is the direction of flow, and we are starting from the extreme upstream point, and it is the distance up to the intermediate sheet pile. So that length is B1. So B minus B1 is equal to B2. Is it clear?
इंटरमीडिएट तो हमारे पास दो पाइल्स भी तो होती हैं, एक अपस्ट्रीम ग्लेसिस पे और एक डाउनस्ट्रीम ग्लेसिस के एंड पे, तो
yes,
उस केस में B1 और B2
no, in that case, you know, at a time you will consider one sheet pile, one intermediate sheet pile, तो उसका ये B1 होगा. Suppose दूसरा sheet pile इधर है, then this would be the B1. Actually the case को आपने देखना है ना. All right, now suppose somebody is interested to determine the uplift pressure at point D. So this is the phi D line and this line. So what do you need to compute? You compute the D over B. So this D is the length of the sheet pile and B is the width of the horizontal floor. So once you have the ratio, suppose this ratio is 0.6, then come here and touch to this line phi D line and then move towards the right. So answer is 40. So 40% of the H is basically the uplift pressure 8 point D. Okay, and if you are interested to determine the uplift pressure here in case 2, when the thickness of the floor, concrete floor, is significant, then this is the line. Then you compute the D over B ratio, whatever it is. Okay, and if this ratio is, let's say, 0.6, so this is the value of the uplift pressure, maybe 28% of H. And now if this is the case 3, it's a case of intermediate sheet pile, then you have to use these lower curves, for which you require the ratio B1 over B. So both are basically horizontal dimensions of the concrete structure, and then these are the values for phi C and these are the values for phi D. So this is point D and this is point C. So what you have to do, for any value of the B1 over B, let's say if it is 0.4, and then you have also to compute the value of the alpha. And the equation of alpha we already know, which we have discussed previously, and you may also find here somewhere. So here is the alpha 1 and alpha 2. So for any value of the alpha and for any value of B1 over B, then you can read, if you are using this graph, then you have to go left and read from here. So that would be the uplift pressure head in terms of percentage. And if you are computing the uplift pressure on point D, which is this one, this was for point C, which is here. This is the location. Okay, if you are computing point C and if you are computing for point D, use this part of the curves, and for any value of B1 over B, and you have to move, and for any value of the alpha, you have to move towards the right. So this is how you can determine the uplift pressures, and how you have to compute the alpha. That is simply the ratio B over D, which is reciprocal of this. Okay. So what is B over D? B is the length of the concrete floor, and the D is the length of the depth of the sheet pile. So in this way, you can have uplift pressures using Kosla's curves. Shall we move ahead?
Yes, sir.
Yes, sir.
Okay. Now, what is the solution given by the Kosla for undermining or for piping? This was the solution of the uplift pressures, that how much are the uplift pressures. So Kosla says that compute the exit gradient. And this is the equation given by the Kosla to compute the exit gradient. Okay. And how we can compute exit gradient? That is H over D. Into 1 over pi under root of lambda. What is the capital H? You know that capital H is the maximum seepage head which is available on upstream side. What is the D? D is specifically the depth of the downstream sheet pile. This is the depth of the downstream sheet pile, not any other sheet pile. जो आखिरी sheet pile है, that is the most important. This sheet pile. To the exit gradient, okay. Then what is the lambda? Lambda is a function of the alpha. And what is alpha? Alpha is B over D. Ratio of B over D is alpha. So I think now you can easily compute the exit gradient. Once you have computed the exit gradient, then you should compute it with what? With the allowable or permissible exit gradient. And over this exit gradient should be less than the allowable exit gradient. So these are the safe exit gradients given by Khosla for several soils which are available under the hydraulic structure in a river or a stream. For example, if it is shingle, the safe exit gradient value may vary from 1/4 to 1/5, means 0.25 say 0.2. If it is coarse sand, it is 0.17 to 0.2, and if it is fine sand, 0.14 to 0.17. By the way, what is happening to the safe exit gradient with the decrease in size of the bed material? क्या हो रहा है? Now here in this direction, the size of the bed material is reducing. And what is happening to the safe exit gradient? वो भी कम हो रहा है?
Yes, sir.
Yes. So these are the safe exit gradients, and this is the exit gradient computed as prescribed by Khosla. So how we can say that our structure is safe in piping or undermining. So the computed exit gradient should be less than this is the safe gradient, safe exit gradient, okay, given by Khosla. So if this is satisfied according to Khosla, the over barrage or any hydraulic structure that is safe against piping or undermining. Is that fine? ठीक हो गया भाई?
Yes, sir.
So this is the solution given by Khosla for the uplift pressures. And the Khosla theory, as I think we discussed previously, you know that Bly's creep theory and lanes weighted theory, they have become now obsolete. Normally we don't use this Bly's theory and lanes theory. कौन सी theory आजकल यूज होती है for the design of such slow in barrages? Khosla theory. Yeah, this is the Khosla theory. Okay. So now come to the corrections. अब ये है कि वो जो the values which we read from curves are the equations. Those are basically isolately we have determined. For example, upstream sheet pile ka portion, and then the intermediate sheet pile portion, and then so on. Moreover, the thickness of floor in two cases, what we have assumed that the thickness of the floor is negligible. So it means we need to apply corrections. So there are three types of the corrections which we have to apply if we are using the Khosla curves or Khosla equations to compute the uplift pressures. The first correction is for the mutual interference of piles. एक pile लंबा है, एक छोटा है. In that case, we have to apply correction. The second correction for the thickness of the floor. For example, in the Khosla's case number 1, how much is the thickness of floor he has assumed? Negligible. In the case number 3, which is the intermediate sheet pile case, again the thickness of floor was assumed negligible. And if there is some thickness of the floor, how to apply corrections. And this is basically if for the case number 2, when there is more thickness of the floor, then how we can apply correction to it. And the C is correction for the slope of the floor. You know that in case of a barrage concrete floor, so there is upstream glacis, and then there is crest, which is horizontal part, and then there is downstream glacis. And if you will see these two glacis, these are basically sloping floors, and we need to apply corrections. So these three corrections have to be applied. Let us discuss the first correction. Correction for the mutual interference of piles. This is the equations to compute correction. So C is 19 root of capital D over B dash D plus B over B. And we know that the B dash, what is the B dash? The distance between two pile lines. If there is one pile here, the another pile here, the distance between them is B dash. And what is B? B, the total floor length. Okay. And what is the capital D? The depth of the pile line, the influence of which has to be determined on the neighboring pile of depth D. So small d is the depth of the sheet pile. Note that D is to be measured below the level at which interference is desired. Where we want to apply correction, so D is measured below to that. All right. For example, if our intermediate sheet pile has certain length and the downstream sheet pile is longer to them, then the D is the, if you draw a horizontal line, the below distance of the downstream sheet pile from this line would be that capital D. And so, you know, all these B dash is the distance between those two sheet piles, horizontal distance. And you can compute this correction. Now, when this correction would be positive, when it would be negative, and that we have to discuss here. The correction is positive for points in the rear or back, and subtractive for points forward in the direction of flow. So in the direction of flow, this correction would be subtractive. And you know, this is very logical. क्यों भाई लॉजिकल है? As we move in the downstream direction, what happens? Head loss बढ़ता है, कम होता है?
So it increases.
Yeah, that's why it should be subtractive. अच्छा, दिस इक्वेशन डज नॉट अप्लाई, हमें करेक्शन ये नहीं लगाएंगे टू द इफेक्ट ऑफ एन आउटर पाइल ऑन एन इंटरमीडिएट पाइल। आउटर पाइल है और ये इंटरमीडिएट पाइल है। इफ द इंटरमीडिएट पाइल की लेंथ जो है इक्वल टू है या स्मॉलर देन द आउटर पाइल है, then we will not apply this correction. Okay, number one. And if it is at a distance less than twice the length of the outer pile, अगर इन दो जो इंटरमीडिएट पाइल और आउटर पाइल का डिस्टेंस ट्वाइस ऑफ आउटर पाइल या डाउनस्ट्रीम पाइल की लेंथ से कम है, even then we will not apply this correction. Okay, now the second correction for the thickness of the floor. And in the standard form profile, the floor is assumed to have negligible thickness. Hence, the percentage pressure calculated by Kohl's equations or graph shall pertain to top levels of the floor. तो ये जो top levels है floor की, उस पे हमें uplift pressure दे रहा है. While the actual junction points E and C at the bottom of the floor. Now you have to see the figure. E1 and C1, hence the pressures at the actual points are calculated by assuming a straight line pressure distribution. Now we want to understand this. So that is given here. If you will see this equation to compute the correction for the thickness of the floor, so this is equal to TF, which is the thickness of the floor, which is this one. So sometimes we also say small d to it. Phi 1 minus phi over d. So what is the d? D is the depth of the sheet pile. जो यहाँ पे sheet pile की depth है, और so this is the depth of the sheet pile. By the way, what is this one? This part. What is this part of the equation? What is phi 1 minus phi 2? This is the difference of uplift pressure between two consecutive key points. Any दो, कोई भी दो key point है, this and that, this and that. तो अगर यहाँ और यहाँ पे हमें पता है, तो divided by d, which is the length of the sheet pile, तो what we are getting this? ये क्या चीज़ आ गई? ये जो मैंने रेक्टेंगल में रखा हुआ है भाई, ये है चेंज इन अपलिफ्ट प्रेशर्स, है ना। तो अगर मैं शीट पाइप की लेंथ से इसको डिवाइड कर दूंगा तो व्हाट आई विल गेट, दिस इज द चेंज इन अपलिफ्ट प्रेशर पर यूनिट लेंथ ऑफ द शीट पाइप। तुम्हें बात समझ आ गई?
यस सर।
पर यूनिट लेंथ ऑफ द शीट पाइप। अब अगर मैं इसको थिकनेस ऑफ फ्लोर से मल्टीप्लाई कर रहा हूं तो इसका मतलब है आई एम नाउ कंसीडरिंग इट्स इफेक्ट के थिकनेस ऑफ फ्लोर पे कितनी चेंज हो रही है ऑफ द अपलिफ्ट प्रेशर्स। सो दिस इज द इक्वेशन, इज वेरी सिंपल, इसमें कोई खास साइंस नहीं है ना। नाउ सिंस द करेक्टेड प्रेशर एट E1, ये अब आपसे पूछना है मैंने, E1 should be less than the calculated pressure at E1 dash. Do you agree? ये E1 dash point है, ये E1 point है। तो E1 पे प्रेशर कम होगा या E1 dash पे ज्यादा होगा, कम होगा? Where the uplift pressure should be smaller.
E1.
E1 should be smaller. What is the reason?
E1 का पॉइंट बाद में आ रहा है तो उससे पहले कुछ हेड लॉस होगा।
इसका मतलब है अगर हम लेट से वो क्रीप थ्योरी भी देखें तो इतना ट्रेवल करेगा पानी तो यहाँ पहुँचेगा ना। सो इट मीन्स के देयर वुड बी सम हेड लॉस एंड ड्यू टू दैट E1 pressure E1 should be less than, the same is mentioned here. अच्छा, अब जो correction to be applied for the joint E1 shall be negative. अब correction कौन सी होगी? अगर मैं E1 पे निकालना चाह रहा हूँ अपलिफ्ट प्रेशर और E1 डैश पे निकाला हुआ है, so correction should be negative. So then I will get the uplift pressure at point E1. अच्छा, what about point C1 and C1 dash? अब मुझे बताएं कहाँ पे अपलिफ्ट प्रेशर ज्यादा होगा, C1 पॉइंट पे या C1 डैश पे ज्यादा होगा?
C1 पे।
C1 पे uplift, yes, it would be more. So the same is mentioned here. Similarly, the pressure calculated C1 dash is less than the corrected pressure at C1. So C1 जो dash है वो कम होगा इधर, इसलिए अब correction, अब हमारी जो hence the correction to be applied at C1 is positive या negative? अब positive चाहिए, है ना? Now the correction would be positive. अगर मैंने यहाँ निकाला है तो मैं उसमें add करूँगा, तो then I will get the uplift pressure at C1. So this is how you have to apply the correction for the thickness of flow. Now the third correction for the slope of the flow. So this correction is applied for sloping floor. As we have discussed earlier, sloping floor कौन से हैं? Upstream glasses of the weir and the downstream glasses of the weir. And this correction is taken positive for the downward slopes. Downward slope कौन सा होगा? जो downward हमारा glasses है. And negative for upward slopes. Upward slope के लिए the correction is negative. तो पहले negative है, बाद में positive है. Okay. Following the direction of flow. So correction factor is to be multiplied by horizontal length of the slope. जो slope है उसकी length हम नहीं लेंगे, बल्कि उसका जो horizontal projection है वो लेंगे like this. So if this is the sloping length, तो हम इसका horizontal projection BS लेंगे. Okay. And divided by the distance between the two pile lines, that is the B1. So that is the B1. So this pile line, this pile line. Okay, this correction is applicable only to the key points of the pile line. Pile line पे लगाने हैं, sheet piles की जो main key point है वहीं, और कहीं apply नहीं करनी है. What is the correction? So this is the correction for slope Fs, that is into Bs over B1. Bs जो sloping length है उसका horizontal component है, और B1 जो है वो that is the length of the floor between जो consecutive sheet pile हैं उनमें horizontal distance है. And what is Fs? Fs is the correction factor for slope. So the values are given here, and they depend on the slope of the sloping component. वजह से 1:1 slope होगा तो correction factor 11.12 होगा, ये वाला Fs. Okay. And if the slope is 8:1, 8:1 means 8 horizontal, 1 vertical. Which slope is bigger? 1:1 slope is bigger or 8:1 is bigger? कौन सा बड़ा स्लोप है?
1:1 sir.
1:1 is a bigger slope. So इस तरफ क्या स्लोप कम हो रहा है या बढ़ रहा है?
डिक्रीज हो रहा है सर.
स्लोप डिक्रीज हो रहा है. और यहाँ पे करेक्शन फैक्टर भी कम हो रहा है या बढ़ रहा है?
डिक्रीज हो रहा है.
डिक्रीज हो रहा है. So means what we can say that जैसे स्लोप ज्यादा होगा, with the greater value of the slope, correction factor for slope would be more. ठीक है, तो ये यहाँ से ये हम वैल्यू लेंगे for any particular slope of the glasses, and then we will apply put here, और ये हम लेंगे तो this would be the correction for the slope. और ये जनाब पॉजिटिव किसके लिए होगी? डाउनवर्ड स्लोप के लिए पॉजिटिव होगी, अपवर्ड स्लोप के लिए नेगेटिव होगी, यानी जो स्लोप की नेचर है उससे ऑपोजिट. ओके, एंड विद दिस वी हैव फिनिश्ड this chapter. So we have discussed the Khosla theory in detail and its corrections, etc. If you have any questions, you are welcome.
सर ये लास्ट स्लाइड में जो डायग्राम बनाई हुई है इसमें सर B1 जो डिस्टेंस है अप टू अपस्ट्रीम शीट पाइल ग्लासेस तक वहां तक है, तो इसकी स्टार्टिंग जो ली हुई है वो सर डाउनवर्ड ग्लासेस पे जो शीट पाइल है वहां से स्टार्ट होनी है या
एक्चुअली यू हैव टू सी दिस स्लोपिंग। आपने करेक्शन कहाँ लगानी है? यस, इन पे लगानी है ना?
यस सर।
बात समझ आइए, आपने लगानी है स्लोपिंग लेंथ पे। अब ये दो स्लोपिंग लेंथ्स है हमारे पास। अगर यही शीट पाइल यहाँ होता तो हम यहाँ से ले लेते डिस्टेंस। अब ये जो करीब तरीन शीट पाइल है, ये कौन से शीट पाइल होंगे बाय द वे? ये वाला शीट पाइल और ये शीट पाइल, ये कौन से होंगे? वुड इट बी, होपफुली दिस शुड बी इंटरमीडिएट, है ना? अगर ये हमारा फ्लोर लेंथ और आगे जा रहा है तो यहाँ पे अपस्ट्रीम शीट पाइल होनी चाहिए। ये शीट पाइल जो है वो इंटरमीडिएट शीट पाइल। हाँ, अगर इंटरमीडिएट शीट पाइल यहाँ पर नहीं दी हुई, देन यू हैव टू कंसीडर दिस शीट पाइल। तो फिर ये आपने ये डिस्टेंस ले लेना है, ठीक है ना? और बी एस जो है, अगर मैं इस पे करेक्शन लगा रहा हूँ तो ये वाली होगी, अगर मैं इस पे लगा रहा हूँ तो ये बी एस होगी। इज दैट ओके?
यस सर।
Okay, with this we have finished this chapter, subsurface flow considerations in barrage design, and I think you are doing this barrage design in the lab as well, and you will apply this Khosla theory over there. And now shall we take about 10-minute rest? अभी पूरे जो है, yes 10-minute rest is fine. कर लें जी 10-minute rest?
ओके सर।
All right, thank you. All right, yeah, are you back? शुरू कर दें जी?
Yes, sir.
Okay. Now we are starting a new chapter. That is the silt control devices. Okay. And by the way, where we want to control silt? In the canals, which we are off taking from the barrage. So we have to control silt. We don't want to allow a lot of entry of silt into the main canals. If a lot of silt will enter into the main canals, then what will happen? If that silt is more than, or those sediments are more than the sediment carrying capacity of the flow, that silt will deposit in the canal and will reduce the cross section of the canal. And then it will reduce the discharging capacity of the canal. So it is very necessary that we should control the silt entry or the silt into the canal. Now let us first discuss few historical examples of silt problems in the canals in Pakistan. The first one was the choking of UBDC, Upper Bari Doab Canal, in 1870. So some portion of the UBDC, there was a lot of sediment deposition and that was choked. The another problem is deposition of silt in Marala Ravi Link Canal. Its depth of flow at that section was 14.5 feet, and out of 14.5 feet, 9 feet was silt deposition. So this was a serious problem. Number 3, silt problem on right side canals of Sakhar Barrage. This occurred in 1938. You know, the Sakhar Barrage was constructed in 1932. and the silt problems in right bank canal of Pottery Barrage. So these are the few examples of the silt problems. And now we want to discuss the silt control. The same as I already mentioned you, that the excess silt entering the main canal has to be prevented. It must be prevented by all possible means. You know, if excess silt gets entered the main canal, then what happens? It deposits in the canal and reduces the discharge carrying capacity of the canal. So now what are the methods to control the silt? These are the 4 methods to control the silt. Number 1, exclusion of silt at entrance. You know, at entrance, when the water is being entered in the main canal, then some of the silt is excluded. And the second is ejection of silt when it is entered the main canal. So ejection means initially we allow entry of the silt or sediments into the main canal, but you know, immediately after a few kilometers we provide a silt ejector, and that silt, extra silt, is basically we offtake and we discharge it on the downstream of the barrage in the same river. Then the third is by proper channel design. If a channel is properly designed, which can carry the silt which comes in suspension, then there are no problems. Number 4, by proper design and setting of outlet. Outlet means head regulator of the main canal. So if it is properly designed and its crest is properly designed in to consider that which part contains less sediments and which more sediments, then we can also control the entry of sediment in the canals. Now we will discuss the number 1, exclusion of silt at entrance. For this purpose, we may require these 3 hydraulic structures. Number 1, divide wall. Sometimes we may require a draining wall. And the second is silt excluder. Okay. Now, first of all, we want to discuss the divide wall, and we know what is divide wall. So the main idea of the to make still water by reducing water velocity, what happens? The silt get deposited, and less silt water that can enter into the main canal. And this divide wall concept was first proposed by Kennedy in 1904. Kennedy also proposed the undersluices. ये जो undersluice हैं, ये भी Kennedy ने propose किए. And the purpose is to flush the deposited sediments. That's why we keep the crest level of undersluice base lower, because we want to flush the deposited sediments. You know that. So this is the silt pocket, and this is the head regulator of the main canal, and this is the divide wall. So these are the undersluice base. And what happens? The velocity of water here is reduced a lot, and due to that reduction in velocity, the sediments, they get deposited here. And annually, what we do when there is a closure period, and then we close this canal, and then we open the gates of these undersluices, and in that way the whole of the water passes from here. We keep close all these gates of the normal base, and in that way this deposited sediments, those are flushed. So divide wall in the river creates a silt pocket, as this is a silt pocket. Okay, as this is our pocket. So what do you mean by pocket? It is closed from 3 sides and open from 1 side. This silt pocket renders top layer of water relatively silt free, So upper layers have less silt, lower layers have more silt. And top layer water, which has lesser silt content, are admitted into the main canal. So that is the purpose of the divide wall. Here in this barrage structure, you can see that this is a divide wall. So these bays are under sluice bays and these bays are normal bays. Now the next is the training wall. Now what is training wall? To understand the concept of training wall, if a barrage is located on a river bend like this is a river bend, then canal head regulator should be located on convex side. So we should provide canal head regulator on this convex side, not on concave side. Why? It reduces silt entry to the canal. If our canal is taken off from the right, from this bank, convex bank, as the silt is concentrated more on inner side, as the silt goes more on the inner side. Now, what is the reason of it? The reason for silt concentration on inner side is the generation of spiral flows or secondary flows. You know, this is a bend, and in this bend, this is the longitudinal direction of the flow, the primary flow direction, and these are the secondary flow directions. And this is the secondary flow direction. So these are the lower layers and the upper layers are like that. So as it moves in this direction counterclockwise, so what happens from the upper layers, on the convex side, the silt doesn't enter much into the canals. But if you will provide a canal on this side, so it will enter from the upper layers into the canals. So if the canals are provided on the inner side of the curvature of the river, then they receive more sediment load. Now, one of the example of such canals, that is the river bend at Sakhar Barrage. So this one is the Sakhar Barrage. The river is coming like this and going like that. So do you think this is basically there is a bend in the river, and which side is convex side? So this is the convex side and this is the concave side. So the convex side river canals, and if this is the direction of flow, so convex side is on which side, right side or left side? Kya bhai? If this is the direction of flow, this convex side is left side or right side?
Left side.
Left side. So on the left side there are four canals on this side, huh? And on the right bank there are 3 canals. So these 3 canals which are on the right bank of the river, these received more silt problem. Okay, but actually these left side canals, they were not receiving more silt and they were running well. So this is a closer view of the Google map. This is the Sakhar Barrage. This is the direction of flow. I mean, this is upstream. And these are the 3 canals which are being taken on the right side. These are the 3 head regulators of the main canals. You can see that. Okay, so these 3 canals were receiving more silt because these were on which side of the bend of the river? These were on the
Concave side.
Concave side. Now what was the solution was given? At Sakhar Barrage, the left bank canals are relatively silt free. How many are the left bank canals? 4 canals. Right bank canals were having severe siltation problem. There was about 5 feet silt deposition by 1938. You know, the barrage was built in 1932. And in 6 years, 5 feet silt was deposited. Means roughly in 1 year there was 1 foot silt deposition, or 0.8 feet silt deposition in the canal. And by 1938 there was 5 feet silt deposition. So that was a serious problem. Now what is the solution given by them? What was the remedial measure proposed at that time in 1938 by the engineers of Sakhar Barrage? So they gave an artificial convex side of the curve on right side. They made an artificial convex bend, because if a convex bend is made, then due to secondary flows, there is less silt entry on that side. And that is called as a training wall. Actually, they propose a training wall. So this is a training wall. So it is up to here. These head regulator of main canals, and also they have proposed and constructed an island. This island was made in 1938. That island closed 10 bays. So this island, so it has closed 10 bays. Once the 10 bays of the barrage are closed, so it means this island reduced the discharging capacity of the barrage. Okay, and in this way siltation problem on the right side canal was solved. Could you follow this? Now once a training wall was provided, so what the training wall and this island has done, they have created a flow, and these canals in that way were come on the convex side of the curvature, which was artificially produced. Okay, so this is the training wall, and this is the role of the training wall. So by providing training wall, we can control silt entry into the canal. Now this is the one more example. This is the which barrage? Kotri barrage. This one is the Kotri barrage, and this is the Indus River flowing in this direction. So what do you think? Is this also on a bend? So if this is on a bend, this side is a convex side of the river, and here there are 3 canals, and these 3 canals, they are relatively silt free. These does not contain too much silt. But this canal, which is on the right side, is carrying a lot of silt. Now, these are the basically structures which we require for silt exclusion. The first structure is divide wall. Second, we may require a training wall. And the third is silt excluder. Now, what is the definition of the silt excluder? The silt excluder is a device or a structure constructed in the riverbed just upstream of the under sluices. Just upstream of the under sluices means in front of the head regulator of the main canal, to exclude silt. What is its purpose? Its purpose is to exclude silt from the water which we allow to enter into the canal. All right, so that is the silt excluder. And what is the principle of the silt excluder? The fundamental principle on which silt control device acts lies in the fact that in a flowing stream, the concentration of silt in lower layer is greater as compared to in upper ones. Okay, so this is the basic principle which is explained here. If you see this channel in which the water is flowing, this is the velocity diagram. Velocity is high on the top layers and reduces towards the, and at bed very low velocity is here. So this is the velocity distribution, and this is the sediment concentration distribution in the channel. So sediment concentration at top is very less, but at bottom is the highest. So how the sediment concentration take place, and what is basically the sediment discharge? That is the water discharge into sediment concentration, and that distribution is like that. So upper layers of water, they carry less sediment discharge, but the lower layers, they carry very high sediment discharge. So the same is explained here. So upper layer, they carry less sediment concentration and less sediment discharge, whereas the lower layers of the flow, they carry more sediment concentration and more sediment discharge. So this was the basic concept, our basic principle. Hence, the device is also designed that the top and bottom layers are separated without any disturbance. And how those were made. Now, this is a Silt Excluder. So, this is the slab of the Silt Excluder. So, water above the Silt Excluder carries less silt, and it is allowed to enter into the main canal. This is the head regulator of the main canal. And the water which contains more sediments, it is allowed to flow in these tunnels, which is basically Silt Excluder. And in this way, the water which carries less silt and water which carries more sediments, that is separated by this slab. All right. So the top water is then led towards the canal. So we allow the top water towards the canal, while the bottom water containing high silt discharge is wasted. Wasted means it is discharged through the under sluices or Silt Excluder. So it means here from this part, which contains more sediment discharge, is basically passed through the Silt Excluder, and from upper layers, which carries less sediment concentration and less sediment discharge, is basically passed into the canal through the head regulator of the main canal. Now, what is the structure of the Silt Excluder? This device basically consists of a number of tunnels. You can see that these are the number of tunnels. Okay. In floor of the deep pocket of the river, running parallel to the axis of head regulator, terminating close to the under sluices. So basically, this structure, what is the location of this structure? So if this is a river and this is the direction of flow, and this is the head regulator of the main canal, this is a very old one and also damaged. So this structure is called as Silt Excluder. So there are tunnels here. This is another tunnel. This is another tunnel. This is another, and so on. So the water which carries more sediment, so it passes, it is separated by this slab, and that moves under the slab, whereas the water which contains less silt is allowed to enter into the head regulator of the main canal. The top level of the roof of the tunnel is kept same as the head regulator of silt. So this level is kept as the same as the sill of the crest of the crest or sill or crest of the head regulator. Okay, same is the case here. So this top level of the concrete floor would be same as the crest level of the head regulator of the main canal. Various tunnels are made of different lengths. So you can see that the lengths are different. It is the longest length, then the length is being reduced as the tunnel distance increases from the head regulator. Again, you can see here its length is the smallest length and it has the longest length of the tunnel. The one near the head regulator being of the same length as that of the width of the head regulator. So whatever is the width of the head regulator, the length is same. And and the successive tunnels being of decreasing length, then the successive tunnels, their lengths are being decreased, like here. So this is of the longest length, and this length they are reducing. Okay, and this is one more basically example, a photograph of the silt excluder of New Khanki Barrage under construction when we visited it. And on this side there is head regulator of the main canal, which was not constructed at that time. And this is the longest tunnel, and these are the how the lengths of the tunnels are being reduced over here. And on this side these are under sluices. Okay. Now could you follow where the silt excluder is provided? What is the location of silt excluder? In front of under sluice base and adjacent to the head regulator of the main canal. So on this portion, basically we provide silt excluder. And what is silt excluder? Those are just series of the tunnels. So how we can make one tunnel? These are the walls and this is the slab. Okay, fine. Now further to understand, this is the plan of a silt excluder. So this is the head regulator of the main canal, and this is the first tunnel, which is of the longest length. Then this is the next tunnel, this is the next tunnel, and the length of the tunnels, these are reducing. And this is the divide wall. So mean these are under sluice base. Okay. And if you will take a section CC, then it will look like this. So here you can see that now we are seeing on this side. So on our this is the divide wall, and this one is the head regulator of the main canal, which is here. And these are the tunnels. So these are the walls of the tunnels, and there are these three tunnels are shown, and this is the slab of the tunnel. The top level of the slab is the same as crest level in the head regulator of the main canal. This is one more plan and section of the head regulator of these silt excluders. Now this one is the head regulator of the main canal, so water is flowing in this direction. So this one is the plan, and this is the silt excluders. These are the tunnels. So this first tunnel is having the same length as the width of the head regulator, but the successive tunnels, then their length is being decreased, and the last one is of very short length tunnel. And this is the cross section of silt excluder, and this is the crest of the under sluice bay, and this is the downstream glasses of the under sluice weir, and this is the water which is moving under the tunnel, and this is the slab of the tunnel or silt excluder, and there is the water here on the and this is the gate. So the water is flowing under the silt excluder, and this is a hydraulic jump here is formed because the here flow is super critical. Now the design of the silt excluder. How much we have to keep the capacity of the tunnels? It is kept equal to the 20% of the canal discharge. Okay, whatever is the canal discharge, we take 20% as the capacity of these tunnels. इनकी capacity कितनी लेंगे? 20% of the canal discharge. Number 2, the tunnels are so designed that a maximum velocity of 2 to 3 meters per second is maintained. Why we keep this much high velocity? To avoid deposition in tunnels. So if I know the velocity in the tunnel, and if I also know the discharge, can't I compute the area of flow required for the tunnels? So number 3, knowing the discharge and discovering velocity, which is this one, the total waterway required for the under tunnels can be determined. Okay. Number 4, the top of the silt excluder slab should be flushed with the head regulator crest. This we already studied. And the height of the tunnel should be 1/3 the depth of water running, including the slab thickness. So how much should be the depth of water? Now, if this is the total depth of the flow when the gates are closed, then it should be 1/3, including the thickness of slab. It should be 1/3. Now we know the height. Whatever is the pond level, we know here in the barrage. So this is the 1/3 of that is the height. So we know the height of the tunnel, the depth of the flow in the tunnel. And we also know the velocity and the discharge. So it means we can compute the waterway total required by these tunnels. Can we compute easily? निकल जाएगा भाई? Do you have any questions? Excuse me. So can you easily design the that how many tunnels are required for the silt excluder? Yes, you can easily design. You will first compute the discharging capacity of the silt excluder. It should be how much? It should be 20% of the canal discharge. जो design discharge canal का है उसका 20% ले लें. And then you have to assume this velocity of flow through the silt excluder, which is 2 to 3 meter per second. Take any value, maybe 2.5 meter per second. Now you know the velocity, you know the discharge. So what you can compute? You can compute the area of the flow. Now you know the depth of the flow because you have to keep 1/3 height of the tunnels, including slab. So it means now you have the depth of the flow. So what you can compute if you know the area of flow? So simply divide the depth of flow to the area, you will get the width of the waterway. Then you decide how many tunnels, number of tunnels do you require. Then just put the number of tunnels and give allowance to the wall thicknesses. Then you will compute the waterway total width of the one tunnel. Okay, this is how you can design the silt excluder. Now, how to design the roof slab? Roof slab should be designed to carry full water load in case the tunnels are empty. Suppose if the tunnels are empty, then the whole load will go to the slab and it must be designed accordingly. The first tunnel should cover completely the head regulator. So it should cover the full regulator. So this is the head regulator and its length should be equal to the width of the head regulator. And other tunnels should be of shorter lengths successively so that we will reduce their length. The discharge through the tunnel will depend upon the head measure above the center line of the tunnel. So discharge, for example, if this is the water level, so the head would be, this is the center of the tunnel. From center of the tunnel to this point would be the head, and the discharge will depend on this head. The tunnel can be treated as box culvert. So this you can keep as box culvert. And the discharge formula for the box culvert is this. Discharge is equal to CA under root 2 GH, which is very similar as the discharge from orifice. Okay. So what is what is C? C is the coefficient of discharge, which you have to determine by this equation. So this C depends on the length of the tunnel. Okay. and hydraulic radius. So it is the C how you can compute. Now please tell me which tunnel would be having more discharging capacity? This tunnel or the last tunnel? Yes.
Close to the head regulator.
This tunnel would be having the maximum discharging capacity. What is the reason?
Reason.
If you see the discharge of box culvert formula, what that formula says? Well, say what the common sense says that the length of this tunnel is the longest. So more friction would be offered by this tunnel as compared to this tunnel. So the discharging capacity of this tunnel should not be lower as this tunnel. What do you think? What is your opinion? Yes, I think the discharging capacity of, even they are of the same dimensions, the cross-sectional area is same. So the discharging capacity of this tunnel should be greater than this tunnel because it has a longer length. So there would be more friction and more head loss. Am I right? You're not responding me.
Yes, sir. Yes.
Yes. Is it? Can you also prove from the equation? So discharge is CD into this thing. So area is same, H is same. Huh? Now see that is C changing, coefficient of discharge. What is this one? Exponent is
-1.
plus half or minus half?
-1.
Minus half. It means the C is equal to 1 over this with plus half, है ना? तो लेंथ
Yes.
के बढ़ने से क्या हो रहा है? C को
Decrease हो रहा है.
decrease हो रहा है. Coefficient of discharge decreases because having more length for this tunnel. तो इसका coefficient of discharge कम है as compared to coefficient of discharge of this tunnel. So the discharging capacity of this tunnel would be lesser as compared to this tunnel. लेकिन वो थोड़ा सा फर्क होगा, ज़्यादा नहीं है. Number 8, the divide wall should be 1.2 to 1.4 times the head regulator. How much we should keep the divide wall? This is the divide wall. ये length of divide wall कितनी होनी चाहिए? 1.2 to 1.4 of the width of the head regulator. This is the head regulator. इससे 20 से 40% ज़्यादा होनी चाहिए. Okay? And now how to compute the efficiency of the silt excluder? So this is the equation to compute the efficiency of the silt excluder. And what is IF? IF is the sediment concentration of the in the river. Okay, this is the sediment concentration in the approach channel or river in ppm. These both. And what is IC? Is the sediment concentration in the canal. Okay, in ppm. What is ppm? Sediment concentration. Suppose if the sediment concentration in the canal is equal to the sediment concentration whatever is in the river, so how much is the efficiency of the silt excluder? कितनी होगी?
0.
Oh, 0. Silt excluder is not doing anything. silt excluder is useless. If the sediment concentration in the canal and sediment concentration in the river, they are same, then what is the function of the silt excluder? It means silt excluder is not performing its function. Okay, so if suppose if the sediment concentration in the canal is 0, which is not possible, huh? 0 means exactly clear water. If it is 0, and if this one is maximum, then how much would be the efficiency of the silt excluder?
100%.
100%. Okay, so this is how you can compute the efficiency of the silt excluder. So do you have any questions till now?
सर
Yes.
सर ये जो सिल्ट एक्सक्लूडर है सर, अगर ये सिल्ट की एंट्री को रोकता है केनाल में, तो सर ये कहाँ, ये किसी टाइम बाद तो ये सिल्ट इसमें जमा होगा, या तो मतलब इसकी क्या मेंटेनेंस है, इसको कैसे रेगुलेट किया जाता है सर, इसके बारे में थोड़ा बताइए सर।
Yes. Where the silt excluder is basically provided? It is provided adjacent to the head regulator of the main canal, number 1, and in front of ये क्या है?
बेस स्लूज,
Under sluice base. Under sluice base. Okay, and usually we keep these close, particularly in low flow season, and then the water is allowed to move from these under sluices, but even then the velocity is reduced here because of the silt pocket, क्योंकि यहाँ divide wall है, here there is divide wall on this side, and these are under sluice, these are also closed, और यहाँ से ये पानी जा रहा है towards the main canal, तो velocities यहाँ कम हो जाती हैं, तो यहाँ silt deposit होती रहेगी. Okay, and then we need to flush it. So for flushing, what you can do, you may close the gates of these under of silt excluder, नीचे से बंद कर दें, and then या खुले रहने दें, and then close the gates of the these head regulator of the main canal, and then allow the water to flow here, so which will flush these whole deposited sediments. So this is how it works. Okay, in normal days the flow is allowed under the silt excluder in these tunnels, which carries high sediment discharges, और जब फ्लो यहाँ से जाता रहता है और सेडिमेंट, मच ऑफ द सेडिमेंट्स आर बीइंग रिमूव्ड, तो यहाँ पे डेपोजिशन भी कम होती है सेडिमेंट्स की, बिकॉज वो निकलती रहती है, एंड देन जो ऊपर वाला पानी है, this water which contains less silt, it is allowed to enter into the main canal. So this is how it works.
Okay sir.
All right. So I think sorry,
एक पॉइंट था कि सिल्ट एक्सक्लूडर का जो रूफ है वो हेड रेगुलेटर की क्रस्ट के साथ होनी चाहिए, तो क्रस्ट लेवल जो है हेड रेगुलेटर वो तो सर काफी ऊपर नहीं है, इस तरह डायग्राम में लग रहा है।
नहीं, यहाँ पे तो नजर ही नहीं आ रहा आपको, जो इसका क्रस्ट लेवल होगा वो यही होगा जो ये टॉप है, देखिए ना, अगर आपने ये सिल्ट एक्सक्लूडर नहीं प्रोवाइड किया, ठीक है ना, तब भी इसका क्रस्ट लेवल आपने ये रखा था, ऊंचा रखते हैं ना, हाँ। अब ये है कि सिल्ट एक्सक्लूडर अगर प्रोवाइड करेंगे तो जो इसका क्रस्ट लेवल है वही इसका होना चाहिए, ठीक।
एक्सक्यूज मी सर। जी सर, ये सिर्फ कनकेव साइड पे प्रोवाइड करते हैं?
नो, इट हैज़ नो कंसर्न विद कनकेव और कन्वेक्स। बेशक आपका स्ट्रेट चैनल भी है, तब भी you want to reduce the silt entry into the canal, and this is the head regulator of the main canal. तो आप जहाँ पे head regulator वाली साइड पे ये silt excluder प्रोवाइड करेंगे, if your river, if your barrage is of taking canals on both side, तो ये फिर दोनों तरफ आप silt excluder provide करेंगे, one on left side, other on right side. Okay? इसका concave convex से कोई ताल्लुक नहीं है. You know, the silt excluder is usually provided even when the river is moving straight. तो पर्पस ये है कि इसका कि थोड़ा लेस सिल्ट वाटर जो है वो हम सप्लाई करें टूवर्ड्स दी मेन कैनाल, और जो ज़्यादा सिल्ट वाला पानी है वो हम नीचे से गुजार दें इन थ्रू दीज टनल्स आर सिल्ट एक्सक्लूडर. यस, किस चीज़ का ताल्लुक है कनकेव साइड से? वो है ट्रेनिंग वॉल. ट्रेनिंग वॉल इज ए सोल्यूशन to reduce the entry of silt into the canal if the canals are taken on the concave side of the bend of the river. Is it clear? वो जैसे ट्रेनिंग वॉल की एग्जांपल आपको दिखाई है ऑन सक्खर बैराज.
यस सर.
दैट इज ओके जी. और कोई क्वेश्चन? That I want to conclude today's lecture, and if you do not have any other question, क्या करें, आपकी एक तो अटेंडेंस भी रहती है ना, अटेंडेंस ले लें, download attendance, and then I would like to leave the lecture. Okay, do you have any question or shall I leave?
No sir, कोई क्वेश्चन नहीं है.
Okay भाई, thank you very much. Allah Hafiz.